Beyond the cloud, beneath the waves, lies the true backbone of our digital world. It's not wireless, and it's not ethereal. It is a physical, sprawling, and colossally expensive network of submarine communication cables, the hidden circulatory system of the 21st century. 99% of all international data, every email, every financial transaction, every video call, travels not through the air, but through these undersea conduits. The sheer physical scale is almost incomprehensible. Over 550 active and planned submarine cables currently crisscross the ocean floors, spanning a combined length of over 1.4 million kilometers. That's enough cable to wrap around the Earth more than 35 times. This is the story of the largest and most critical engineering project in human history, an endeavor of unprecedented logistical complexity and immense corporate power. This monumental network is not a public utility. It is overwhelmingly owned and operated by a handful of mega corporations. Tech giants like Google, Meta, Amazon, and Microsoft have transitioned from being mere customers of this infrastructure to its primary architects and finance. Google alone has investments in over 20 subsea cables, totaling more than 150,000 kilometers of private network capacity. Their Grace Hopper cable, connecting the US, UK, and Spain, is a 16-fiber pair system, a significant engineering leap designed to carry a staggering 350 terabits of data per second. Similarly, Meta's to Africa cable is a Leviathan project. At 45,000 kilometers, it is one of the longest cables ever deployed, designed to circumnavigate the entire African continent and connect it with Europe and the Middle East, involving a consortium of telecom operators but driven by Meta's strategic vision and financial muscle. The investment required is astronomical. A single transatlantic cable can cost anywhere from $300 million to over $600 million to design, manufacture, and deploy. These are not public works. They are private corporate assets, strategic arteries of global commerce and communication, controlled by boardrooms in Silicon Valley. The manufacturing of a submarine cable is a marvel of materials, science, and precision engineering. At its core are the impossibly thin strands of optical fiber, each no thicker than a human hair. These are made from ultra-pure silica glass, so transparent that if the ocean were made of this material, you could see the seabed from its surface. These delicate fibers are the data conduits. They are bundled together. Modern cable might contain up to 32 fiber pairs and, then encased in a series of protective layers. First comes a thixotropic jelly to cushion the fibers and repel water. This is followed by a copper or aluminum tube that not only provides structural integrity but also carries the high voltage electricity, often thousands of volts, needed to power the inline amplifiers or repeaters, spaced every 50 to 80 kilometers along the cable's length. These repeaters are sophisticated optoelectronic devices that receive the light signal, convert it, amplify it, and retransmit it, preventing the signal from degrading over thousands of kilometers. Finally, the entire assembly is sheathed in layers of steel wire armor and a tough polyethylene jacket. The final diameter of a deep-sea cable is often no thicker than a garden hose, yet 4 sections closer to shore where risks are higher. The armor is substantially thicker, making the cable as wide as a soda can. Laying this cable is a logistical ballet performed on a global stage. Specialized cable-laying ships, costing hundreds of millions of dollars each, can carry up to 9,000 kilometers of cable in their massive temperature-controlled holds. The process begins with a highly precise survey of the ocean floor, using sonar to map the terrain and identify the safest route, avoiding volcanic vents, steep cliffs, and unstable seabeds. The ship then proceeds at a slow, steady pace of about 10 kilometers per hour. A specialized sea plow is often used in shallower waters, up to 1,500 meters deep. This underwater vehicle is dragged along the seabed, simultaneously digging a trench and feeding the cable into it, burying it for protection. In the abyssal plains, miles below the surface, the cable is often laid directly onto the seabed, where the risks are lower. The entire operation is a continuous 24/7 process that can take weeks or even months for a single transoceanic crossing, with the crew working in shifts to manage the immense tension and precise navigation required. Despite this meticulous engineering, the network is perpetually vulnerable. The deep ocean is a hostile environment. While the infamous shark bites of early cable lore are now rare thanks to tougher sheathing, the primary threats are man-made. Over 70% of all cable faults are caused by commercial fishing trawlers and ship anchors dragging along the seabed. A single, careless anchor drop in a high-traffic shipping lane can sever a link, disrupting internet connectivity for millions. Natural disasters also pose a constant threat. Submarine earthquakes and underwater landslides, like the one that triggered the 2006 Henshin earthquake off the coast of Taiwan, can snap multiple cables simultaneously, causing widespread outages across entire regions. Repairing a severed cable is a monumental task. A repair ship must be dispatched to the fault location, which could be in the middle of an ocean. Using a remotely operated vehicle ROV, engineers locate the 2 broken ends of the cable on the seabed. A specialized grappling hook is used to retrieve each end to the surface. On board the ship, technicians meticulously splice the hair-thin optical fibers back together, process done by hand in a sterile cleanroom environment before sealing the repaired section in a waterproof joint and carefully lowering it back to the ocean floor. A single repair operation can take over a week and cost millions of dollars. The data throughput of this network dwarfs any other communication technology. Satellites, while vital for remote areas and broadcasting, suffer from high latency and limited bandwidth. The speed of light in a vacuum is fast, but the distance to geostationary orbit and back introduces significant delay. Light traveling through fiber optic glass is slightly slower, but the path is thousands of times shorter. A modern submarine cable system can transmit data at rates exceeding 400 terabits per second. To put that into perspective, that's the equivalent of streaming over 80 million high-definition movies simultaneously. This colossal bandwidth and low latency are what enable the instantaneous, data-rich applications that define modern life, from high-frequency financial trading to real-time cloud computing and global video conferencing. The entire satellite communication industry's total bandwidth capacity is just a tiny fraction of what a single new-generation subsea cable can carry. The points where these global arteries make landfall are some of the most critical and heavily guarded pieces of real estate on the planet. These are the cable landing stations. They are typically unassuming, windowless buildings located on coastlines, often semi-camouflaged. But inside, they are fortresses of technology and security. Here, the submarine cable terminates, and the high-voltage power is converted and fed into the cable. The optical signals are demultiplexed and transferred to the terrestrial fiber network. These stations are hubs of immense data flow, connecting the subsea link to the national internet backbone. Security is paramount. They are protected by high fences, advanced surveillance systems, and 24/7 monitoring. The geographical placement of these stations is a matter of intense strategic importance. Cities like Bude in the UK, Marseille in France, and Singapore have become global data crossroads, not by chance, but because they are the nexus points for dozens of intercontinental cables. Control over these landing points is, in effect, control over the flow of data for entire continents. Ultimately, the global submarine cable network is the unseen monument of our age. It is a testament to our species' relentless drive for connection, a feat of engineering that rivals the pyramids and the space race in its ambition and complexity. It is the physical manifestation of the internet, a tangible web of glass and steel that binds our global economy and society together. While we live our lives in the wireless cloud, we are fundamentally tethered to this deep, dark, and powerful infrastructure. It is a system built on staggering financial investment, logistical genius, and the strategic foresight of a few powerful corporations. This hidden network is not just a part of the modern world, it is the foundation upon which it is built. Thank you for watching Deep Files. If you found this exploration into the world's hidden infrastructure fascinating, please like this video, subscribe to our channel, and hit the notification bell so you don't miss our next deep dive. See you next time.